So our next speaker is Agnian Trifonov from South Carolina, who will speak on covering systems. Please.
Thank you. So I want to thank the organizers. It's a great conference they have put together. So covering systems, so I want to talk mostly about distinct covering systems. So you have a system of congruences, and you require the moduli to be distinct, so you can order them. Let's say N1 is the smallest, Nk is the largest, it's going to be a finite system. And that's going to be a covering system if each integer satisfies at least one of the congruences. So in our notations, N1 is going to be always the least modulus, and the largest one we're going to denote by capital M maximal. And the LCM of the moduli is going to be capital L. So this covering system always appears, well, almost always in talks about covering. So it's probably one of the first distinct covering systems that ever appeared. So first one, you cover the odd numbers. After that, 2 mod 4, you're left with the numbers which are 0 modulo 4. That splits into 3 classes modulo 12, 0, 4, and 8. So you can use 3 congruences, 3, 6, and 12 to cover them. So it's kind of wasteful with 3 and 6, but well, you can do it. Erdős introduced the use of coverings in number theory in the 50s. And we saw the previous slide, we had a covering system with minimal modulus 2. Erdős constructed a covering system with least modulus 3 and largest 120. Swift increased that to 4 and later on with 6 for smallest modulus. That was improved through the years. Churchhouse constructed one with smallest modulus 9, Krukenberg 18, after that 20, Morikawa 24, in a mysterious paper that was hard to find in some Japanese journal. In another 25 years, Gibson improved that from 24 to 25. And then Pace-Nielsen made a big jump from 25 to 40 by introducing sort of use of recursive techniques into coverings. Recursion into coverings, so techniques from computer science to coverings. And his student, Owens, improved that to 42. Erdős wrote, it seems likely that for every C, there exists such a system that all the moduli are greater than C, which became the minimum modulus problem. In 1981, Erdős and Graham conjectured that for any constant greater than 1, if you consider system of congruences with moduli between n and c times n, think of C large, then the density of the uncovered set is at least epsilon that depends on C. Positive density remains uncovered. So you're not going to, if n is sufficiently large, you're not going to be able to construct a covering. Moreover, there will be a certain proportion that is going to be left uncovered. And that conjecture was proved in a strong form by Filossetta, Ford, Koniagin, Pomerance, and Yu, and they proved many other nice results in there. A few years later, Bob Huff added several crucial ideas to their work and made a real breakthrough. Nobody expected that, but in 2015, he solved the minimum modulus problem and showed that if you have a distinct covering system, the smallest modulus is at least 10 to the 16. Also in the 50s, Erdős and Selfridge posed the odd covering problem, whether there exists a distinct covering with all moduli distinct odd integers. A work of Ballister, Bobas, Morris, Sahasrabudhe, and Tiba brings us closest to solving this problem. So they show that if you have a distinct covering, then either one of the moduli is divisible by 2, or one is by 9, or one is by 15. So if you remove the two ors, then you're going to have the odd covering, a solution to the odd covering problem. So the authors also improved on Bob Huff's bound. They showed that the least modulus of a distinct covering system does not exceed 606,000. And also they show that there is no distinct covering system in which all moduli are odd square-free integers. So they solved the odd covering problem, assuming that all moduli are square-free numbers, which is not easy to do. So in the last 15 years, we saw a number of truly remarkable results on covering systems about what is not possible. What about results on what is possible, or what is the best possible in certain cases? In 1971, Krukenberg, a student of Selfridge, wrote a very nice dissertation on coverings. He was at the University of Illinois at Urbana-Champaign. Unfortunately, his results were never published. So here are some of his main results. So he showed that if the first smallest modulus, so in what follows, C is going to denote distinct covering system. So if you have a smallest modulus 2, then the largest one is at least 12. So you're not going to construct a distinct covering with moduli in 2 to 11. That was sort of known, but he wrote a proof for that. So maybe in the fall course, so he wrote a rigorous proof. So if N1 is 3, then you have to go at least to 36 to construct a distinct covering system. So he did that with proof. N equals 4. If you start with smallest modulus 4, you have to go at least to 60. And Krukenberg-Rice, the result is best possible, but we will not be proved here. Unfortunately, I haven't seen a proof in the last 50 years appear. So then after that, he constructed a covering starting with 5 up to 108. So without any claims whether 108 is the best, he says, well, it may be the best, but he's not sure. He also constructed covering systems with smallest moduli from 2 to 18, while keeping the LCM relatively small. So he tried to keep the construction kind of compact without increasing the LCM of the moduli much. And also he constructed a distinct covering system with square-free moduli, not using the modulus 3. So he skipped 3. 3 was never used in his system. And it's quite a covering system, hundreds of coverings, not using any recursion. And also, he gave a complete description of distinct coverings of when you only use the primes 2 and 3. So the LCM is of the form 2 to the power a times 3 to the power b. So he showed that the smallest modulus has to be at most 4. If it is 3, then he gives a description when this can happen. And also he gives a description when this can happen if the modulus is 4. So he completely analyzed what can we do if we have 2 primes. We only use 2 primes. He used other pairs of primes, but they're not so interesting. You cannot do much with just 2 primes. Now, without few loose ends left by Krukenberg. So first of all, I showed that if you start with 4, then indeed you have to go all the way to 60. So it's kind of takes a little bit of work because we get very close. So if you go from 4 to 59, you miss just by a little bit constructing a covering. So it's kind of a delicate argument. A covering with smallest modulus 3 and LCM 120 was constructed by Churchhouse, and showed that that's the best possible. If you pick a LCM less than 120, that's not possible. That's not difficult using the description of the congruences with LCM of the form 2 to the power a times 3 to the power b. And you have a few more that are easy to analyze. If you start with 4, Krukenberg constructed a covering that has LCM 360, and I showed that indeed that is the best possible. We cannot stop less than that. So when he took care of constructing small LCM, in this case, he constructed something which is best possible. What are some of the tools that are used to prove that? So basically, one tool is the following. So suppose that you have a covering, doesn't have to be distinct, and you have a prime that divides one or more of the moduli. And suppose that the congruence with moduli divisible by this prime are written in this form. So I decompose it into part that is mod p and a part that is something which is not divisible by p. And you can state this lemma into more general form if you have p to the alpha, but for simplicity, I write it down just for p. And then you split these congruences into bins. So basically in the Jave bin, you put the congruences within which are in the class X congruent to J modulo P. And then dump the part that is modulo P. So basically you're going to have this congruences, the first part of the congruence into these different bins. Then one can replace the congruences divisible by P by the intersection of the congruences that you have in these bins, modulo P. So for example, let's consider a couple of examples. So If you have that 7 times 1, 7 times 2, and so on, all the way to 7 times 6 are the only moduli divisible by 7, we can simply discard them and still have a covering, if you do have a covering, because you have 6 congruences that you put into 7 bins. One of them is going to be empty. The intersection is going to be empty, so you just discard that. So this is something that Krukenberg knew. Another example, suppose now let's add one more congruence. Now let's put 7 times 8 so that we have exactly 7 congruences. Then the only way to get non-zero intersection if you put them in different bins, so then the intersection is going to be 120, the LCM of this, so we can replace these 8 congruences by a single congruence modulo 120. Now, if you have, so it works great if you have less congruences or the same number of congruences as the prime. What if you have a little bit more congruences than the prime? You can still say something in that case. For example, let's say you have a covering where the only moduli divisible by 3 are 3, 6, 12, and 15. Well, you put them in bins, so obviously you have to put one in one bin. It's not going to help you anything to put something together with one. Then you have choices. You can leave 2 and 1 and put 4 and 5 together. Then you can replace your 4 congruences by 2 congruences modulo 4 and 10. But you have to be careful later on to make sure that they're in the same class modulo 2 because you took intersection with the bin mod 2. Or if you leave 5 alone, then with 2 and 4, you're going to get 2 congruences modulo 10 and 20, which you may say is worse. But here the restriction is that they have to be in the same class modulo 5. So in a sense, the restriction is different. So when you talk about coverings, you still have to consider this class, this case. So it's not going to help you construct any coverings or anything, but it's something to be considered. So you can say something and reduce the complexity of your system when the number of moduli divisible by the prime is close to that prime. And the other technique that we use, one of the other techniques, is that reduction modulo P. So basically, suppose we have a covering and let P be a prime dividing the LCM, so sum of the moduli. So because this is a covering, it's going to cover not only all the integers, but arithmetic sequences of the 4m times P plus A, so A is fixed. So therefore, if you substitute MP plus A into the congruences that we have in the covering and solving, well, we have several cases. If the modulus is relatively prime to P, the modulus is not going to change. We're going to get some congruence for M. You can write down what it is explicitly, but it doesn't matter. So this is if P does not divide the modulus. If P divides the modulus and your congruence is not in the right class modulo P, there's no solution. So you're going to lose this congruence. Or you're going to get the congruence modulo Ni over P in case your congruence is in the right class modulo P. Thus, we obtain P coverings out of the original one, where the moduli not divisible by P can be used in all P coverings, and the moduli divisible by P get divided by P and can be used just once. So for the first theorem to show that there is no covering from 4 to 59, you can, first of all, you trim down the number of moduli using the first two to 17, I believe. And after that, you reduce modulo 3, and you need to construct 3 coverings, and turns out that you can. Then you try to build back your congruence from that, and you see that there is some compatibility solution that you need to be careful to follow. So basically, in that case, you have 2 congruence modulo 20 and 40, which in one case, you want them to be modulo 5, but in the other of the 3 congruences, you need them to be in distinct classes modulo 5. And when you do this restriction, this reduction modulo P, it preserves 2 congruences being in the same class modulo different primes. So that is what is the problem, and that's why we fail to construct the covering with moduli from 4 to 59. We just miss it by a little bit. So if you add 120, it may be possible to add 240 instead. We will be able to construct the covering. Okay, now what's left out of the monumental work of Krukenberg? Well, first of all, this n equals, if you start with 5, can you go all the way to 108? In the covering of Krukenberg, there's some loose ends, so sometimes you're forced to use moduli to cover certain quasis with some waste. So let's say something will be covered by a Congress module of 48, you use 24 for that. But on the other hand, for some structural purposes, you pretty much have to do it. So if I had to bet, I would say probably 108 is the best possible. So this is doable problem, but it will require some amount of work. Second, would be interesting to be able to describe all coverings when you can use 3 primes. Now, we have many cases for the exponents, so for practical purposes, probably makes sense to require the power of 2 to be the largest, then B, then C. And this is doable. It will require some amount of work, but it's quite doable with the tools. With the paper that I have, is on arXiv. Also, Krukenberg constructed a covering with smallest modulus 5 and LCM 1440. Is this the best possible? That one I haven't worked much on. So that once you do 2, that should come pretty easily. And fourth, proof or disprove that there exists a covering, square-free covering with smallest modulus 3 and all moduli square-free integers. So in other words, you're only missing the modulus 2. You're allowed to use all square-free integers but 2. So to show that no such covering exists is going to be very hard, because even to show that to solve the odd square-free covering problem was quite hard. Here, you're allowed to use all even square-free numbers except 2. So, and constructing one is not clear. So I know several people who are very good with coverings who tried to do it and couldn't succeed. So Krukenberg started constructing one in his dissertation. For a while you tread water, but eventually you start losing ground. So the way he tries to do it, he says it's not going to work, but can you improve somewhere along the way? It's not so clear. So that is a hard problem. This is the hardest one of the 4. And then recently thinking about why can't we cover, why the minimal problem covering problem has a solution? Why can't we cover the numbers if we start with big modulus and go very far? And that got me to the following problem. How many times can we cover the integers? So let n be a positive integer. And let CFN be the largest number of times we can cover the integers using congruencies with moduli 1, 2, 3 through n. So obviously, C of 1, we can use only the congruence module 1. Everything is covered just once. From 2 to 11, well, you cannot, from Krukenberg's work, we know that we cannot construct a covering from 2 to 11. So using the modules from 2 to 11, there will be something uncovered. So C of 2 to C of 11 is going to be still 1. Once we get to 12, we can cover the integers twice, because we can construct a covering using the moduli from 2 to 12, and 1 is going to cover them one more time. Krukenberg constructed a covering with smallest modulus 13 and largest one 4 billion and change. So that is at least 3. Also, this quantity is non-decreasing function. So if you can cover a certain number of times the integers with moduli from 1 to n, if they give you extra congruence, you can certainly are not going to do any worse. Moreover, from the work of Ballister and his co-authors, we know that from 606,000 on, we cannot construct a covering using this moduli. So therefore, from 606,000 to n, there will be at least one number which is not covered. Maybe it will be very unlucky and hit by all the numbers up to that. So C of n is going to be at most that much. In reality, first of all, for the minimum modulus, there is a folklore that people believe that it's going to be at most 100. So I would expect that you can cover the integers no more than 10 times using this construction, using the moduli from 1 to n, no matter how big is n. But again, I just thought about this for a couple of days. This problem came to me a day or two ago. So that's what I have for now. So an open problem is find this limit. So what is how many times we can cover the integers? A variation would be, but this doesn't have much to do with covering, and I don't think is the right problem to think about. But anyway, so if you have time, you can think of covering not all integers, but covering just the numbers from 1 to n using the congruencies from 1 to n. How many times you can do it? But again, this is not right in the context of congruencies, but still is combinatorial problem. So, and the answer may be completely different and the behavior may be different. I haven't given any thought to that. And also another variation is how many times can we cover the integers by using infinitely many congruencies. So you're allowed to use congruence module 1, 2, 3, and so on, but going to infinity. So can we cover them infinitely many times? And it's quite possible that the answer may be yes. Note that there is a big difference between finite and infinite coverings. Now, if you start with the smallest modulus 606,000 or more, no matter how far you go, you're not going to be able to construct the covering. On the other hand, no matter how big number you give me, say 100 billion, if you allow me to construct an infinite covering, it's quite easy to construct not only one, but I believe many. So I can split this set to disjoint classes and using the moduli in these classes as moduli for some congruencies cover the integers. So I sort of have a construction in mind, but I have written it on paper so that the answer is infinity. So anyway, so let's say it's conjecture that is infinity. And given that this is the last talk for the day, so probably this is a good place to stop. So thanks again.
Thank you very much. Are there any questions? Looking. If not, thank you